Now let's try to understand how CPU interacts with memory. This is my CPU and this is my memory. There has to be some specific procedure by which CPU asks from memory and memory responds. Whenever CPU goes to memory, it says two things: which data it wants to read or write. Second is for what purpose it wants to access the data, whether it is for read or it is for write. For what purpose it is. To understand this, let me have a practical example. When you are at your home and you want to read some book, now you order your servant to bring out some book from drawing room. You have to tell your servant that which book you want, where it is located. You have to tell the precise location, like it is on 4th shelf from the top and 5th book from left. Like that, you have to tell a precise location. Otherwise, your servant won't be able to retrieve that book. Similarly, in case of CPU tells the precise location. When I say that which data it wants to read, I mean to say that what is the location or address. Now scenario is like this: CPU wants to issue some command, then it has to tell that what is the address and whether it is for read or write. These two things has to be mentioned by CPU. Now question is, what do I mean when I say address? What is address here? For what? To understand that what kind of addresses I am talking about, we need to understand how memory looks like and how we can address some data in memory. You can view memory as one large array of many locations, and each of this location is called cell of the memory. So if there are 16 cells, then how many bits I need to represent 16 cells? I need 4 bits, from 0000, 4 zeros to 4 ones. In these 4 bits, I can represent my 16 cells. Okay. Now let's say these are 16 cells. Now address of first cell will be 4 times 0 and address of second cell will be 0001. Similarly, address of last cell will be 1111. In general, if there are 2 to the power n cells, then I need only n bits, n bit address. If there are 2 to the power n cells, then I need only n bit address. Now if someone asks me that what is size of memory, then I will say number of cells, that is 2 to the power n, into number of bytes in each cell. That is nothing but cell size. For example, if there are 16 cells and each cell has 1 byte, then total size of memory is 16 byte only. This is size of memory. I will sometime use that memory is byte addressable. This is just a fancy way of saying that each cell size is 1 byte. If I am saying that memory is byte addressable, this is just a fancy way of saying that each cell size is 1 byte. Okay, so far so good. I have understood that if each cell size is 1 byte and there are 16 cells, then memory size will be 16 bytes. Similarly, if there are 2 to the power n cells and each cell size is 1 byte, then memory size will be 2 to the power n bytes. Now the question is how we store data in memory. Let's say I have 4 byte integer. Size of the integer is 4 byte. I am using hexadecimal notation because in binary 4 bytes means 32 bits and I have to represent 32 ones and zeros. To avoid this only, I am using hexadecimal notation. Let's say I have an integer. This is in hexadecimal notation, and in hexadecimal notation each digit represents 4 bits in binary. Hence these 2 digits is nothing but 8 bits, that is 1 byte. And I have such 4 pairs. So this is the integer of 4 byte. Now I want to store this integer at the address, let's say 0111. Now it is clear that this is 4 byte integer and my cell size is only 1 byte. So I have to store this integer into 4 cells. In this one, this one, this one and this one. Now these are my 4 cells and this is my integer. Here integer is of 4 bytes. 1, 2, 3rd and 4th. This is my most significant byte and this is my least significant byte. For you, it might look natural that storing 90 at the lowest address. This is my lowest address and this is the highest address which I am going to use to store this integer. Now storing 90 at the lowest address might seem natural to you, and following 5C here and then AB and FT. This might look natural to you, but this may not be natural to me or to someone else. I may want to store this 5D at the lowest address. I may want to have order like this: 5D at the lowest address and then AB and then 5C and 90. These are the two different ways by which I can store my data that is more than 1 byte. If it is of only 1 byte, then there is no problem. I will store in only one cell. But if it is of more than 1 byte, then I have to decide whether my MSB will go to lowest address or my LSB will go to the lowest address. Don't think like that there are 4 cells and there are 4 bytes, so I will have some combination like 4 factorial ways to represent. No, there are only 2 ways. We are not going to play a combinatrix game here. We just have 2 ways. Either we represent MSB at the lowest address or we represent LSB at the lowest address. We can classify these ways into 2 types: Little Endian and Big Endian. Big Endian say that store your MSB at lower address. Little Endian says that store MSB on higher address. This is my lower address and this is higher address. Now you can identify that under which Endianness this storage is coming. This is Little Endian or Big Endian. Similarly, this is what? As you can see here, 90 is MSB and 90 is stored at lower address. So store MSB at lower address, hence this is Big Endian. And this is Little Endian. You can remember like this: this is my big end of data, and this is my little end of data. If I am storing the data from big end, I am storing like 90, 5C, AB and FT. So I am storing from big end. And if I am storing my data from little end, then it is Little Endian. And if I am storing my data from big end, from this end, then it is Big Endian. Nothing much to worry about these representations. These are very simple. Now whenever we have 2 choices of something, question comes which one is better. Either Big Endian is better or Little Endian is better. Answer of this question is nothing. That is, no Endianness has any advantage of other. That depends on processor, that which Endianess it is using. Now let me ask a reverse question. You are already given some data that is stored in memory. Let's say 12 is stored at 1000 address and AB is stored at the next address, and similarly CD is stored at 1011. Now you are asked to fetch this data into register. Let's say CPU wants to fetch this data into register. The register is 4 byte size. Now if the processor is following Little Endian, then how will it retrieve this data into register? And if the processor is following Big Endian, then how will it retrieve the data into register? The idea is simple. In Big Endian, the lower address byte is your MSB. So 12 will come here and remaining bytes will come accordingly. AB will come here, 34 and then CD. But in Little Endian, lower address byte is LSB, not MSB. So 12 will come here and then AB, then 34 and then CD. This is about storage of data using Little Endian and Big Endian. The idea is very simple. In Little Endian, LSB stores at lower address, but in Big Endian, MSB stores at lower address. That's all. We are getting clarity about how CPU interacts with memory. If this is my CPU and this is our memory, CPU places address of some location that it wants to access. Now at that particular location, CPU either may want to read or may want to write. If CPU wants to write, then data will go from CPU to memory, and if CPU wants to read, then data will go from memory to CPU. So this is my address bus on which CPU places address of the location it wants to access, and this is my data bus on which data flows. Either it goes from CPU to memory in case of write, and it goes from memory to CPU in case of read. If you notice, then you will see that address bus is unidirectional, but my data bus is bidirectional. Why? Because data can flow either from CPU to memory or memory to CPU, but memory cannot give address to CPU. CPU is only master and CPU will give address to memory. That is why it is only unidirectional. But along with these two lines, there is one more line also. That is my control line. My control line defines that it wants to read or it wants to write. Okay. Now you might say that it must be unidirectional only, because CPU gives control to memory. Memory cannot give control to CPU. CPU tells memory whether to read or to write, but it is bidirectional. Why? Because in case some problem happens, then memory should also able to intimate CPU by control lines. Memory should also send some controls to CPU that this particular location is not accessible, maybe because of protection and maybe because address is invalid, anything like that. It so happens that this control line is also bidirectional. Why so? Because CPU to memory is clear. Why? Because CPU wants to give control to either read or write. But why memory to CPU? Because memory may sometimes also give control to CPU that this particular address is not accessible because of some reason. Till now I have been talking about byte addressable memory, means each cell is storing 1 byte. Whenever I am saying that it is byte addressable, it means that I can address each and every byte, nothing lower than that. The smallest addressable unit is byte only. See, I have address of each cells, right? And each cell is storing what? 1 byte. So I can address each byte. Now the question is, can memory store more than 1 byte in one cell? Yes, it can store. Let's say it is storing 2 bytes in one cell. It is storing 2 bytes in each cell. Now if there are 2 bytes in each cell and I have address of one cell, can I address each and individual bytes? Question is this. I cannot address each and individual bytes, but I can address each and individual group of 2 bytes. Why? Because my cell size is 2 bytes. So I have address of this cell, I have address of this cell, I have address of this cell. This means that I can address each 2 bytes. But let's say there are 2 bytes one byte is this and one byte is this. Now if I want to address this particular byte, now I cannot address this particular byte, but I can have address of these 2 bytes. So here in this case, if cell size is 2 bytes, then smallest addressable unit is 2 byte only. Whatever is my cell size is my smallest addressable unit, because I can address each and individual cell, nothing lower than that. So in this case, it becomes 2 byte addressable memory. Sometimes you might also see that memory is word addressable. Now I am going to familiarize you with word addressable memory. To tell you what is word addressable memory, I need to tell you that what is word itself. What is this? Word is something that CPU always asks for. CPU don't care my cell size. CPU always asks for one word. If let's say CPU word size is 4 bytes. So whenever it places an address to memory, it doesn't care what your cell size is, what memory cell size is. It always expects data of 4 bytes in return. CPU always asks for a word. It doesn't care your memory cell size. It doesn't care your memory is byte addressable or 2 byte addressable or word addressable. It only cares that it always wants one word in return. For particular example, let's say my cell size is 2 bytes but my word size is 4 bytes. Then at every request, memory has to return 2 cells, because my cell size is 2 bytes and word size is 4 bytes. So memory has to return 4 bytes. To accomplish this, memory will return 2 cells. In other words, CPU don't care what is memory configuration. It always asks for one word, and memory also always has to return one word irrespective of their cell size. If let's say cell size is 1 byte and word size is 2 bytes, in that case memory has to return 2 cells at every request. Now you can easily guess, when I say word addressable memory, then what do I mean? I mean that cell size is 1 word. If I am saying that byte addressable memory, then cell size is 1 byte. If I am saying that 2 byte addressable memory, then cell size is 2 bytes. If I am saying that word addressable memory, then cell size is 1 word. That's all. And the important thing to notice is that CPU does not care about your memory configuration. It always asks for one word only. I hope that you have some basic idea of what is word addressable and what is byte addressable. These word and byte addressable, that implies to memory only. CPU do not care about memory configuration. It always wants one word. Okay. Now let's have an example of valid sequence of addresses that CPU can generate. Let's say initial address that CPU generates is 1020. I am using decimal number here to make my things simpler. If I use binary, then it will be overhead of unnecessary calculation. Therefore, I am using decimal number. So 1020 is my initial address that CPU generates. And let's say word size is 2 bytes. Now question is, what will be my next sequence of addresses that CPU will generate if memory is byte addressable? And similarly, what sequence of addresses that CPU will generate if memory is word addressable? This is my memory, and CPU generates address of first location, let's say 1020. Now if memory is byte addressable, then each cell will contain 1 byte only. So each cell is containing 1 byte. Now next address is 1021 and then 1022 and then 1023. So the question is, what will be the next address that CPU can have can CPU have address of 1021? Can CPU place address of 1021? The answer is no. Why? Because word size is 2 bytes, so CPU will be accessing 2 bytes. Whenever it is saying 1020, then it will access 2 bytes following 1020 and 1021. So next address will be 1022, not 1021. 1021 will not be valid address, 1020 is valid address, and next 1022 is valid address. Why? Because CPU always address a word, and a word is consisting of 2 bytes. Hence, once CPU generates address of 1020, now next address will be 1022. And similarly next address will be 1024. Okay, but in case of byte addressable, things will be different. How? Let's say my memory is this. Address of first cell is, let's say, 1020, then address of this cell will be 1021, address of this cell will be 1022. Now if you notice, address of cells are always in sequence. It do not depend that memory is word addressable or byte addressable. Address are always in sequence, because let's say I am representing my address with 4 bits and first cell address will be 0000. Now next cell address will be 0001 irrespective of the cell size. Cell size may be a word or byte or 24 bits or 16 bits, anything. The address of cells will always be in sequence. First address cell will be 0000, the next address cell will be 0001 and the next address cell will be 0010 irrespective of the cell size. So here the cell size is word, because memory is word addressable, hence the cell size is 1 word. But the address of the cells will always be in the sequence. So in this case, every cell is having 1 word only. Now if CPU plays first address 1020, now can you guess that what will be the next address? As we know that CPU always address words. So after having address of first word, address of second word is only 1021. It is not 1022. This is the third word. This is third word, right? This is second word, and address of second word is 1021 only, and address of third word will be 1022. So these are the valid address here. Here the valid addresses are in sequence, but here the valid addresses are not in sequence. It depends on what is word size. If word is consisting of 2 bytes, then this is my first word and this is my second word. So address of first word will be 1020 and address of second word will be 1022, not 1021, right? So this is my valid address. Why? Because this is address of first word, and this is also my valid address because this is address of second word. This is not address of any word. This is address of some byte that is irrelevant. Similarly, in this case, this is address of first word, this is address of second word. Hence, these are the valid addresses that CPU can generate. And similarly, these are the valid addresses that CPU can generate: 1020, then 1022, then 1024. 1021 or 1023, these are the invalid addresses. CPU cannot generate these addresses. Now, I hope that you get a clear idea what is word addressable, what is byte addressable, and what are the some valid range of addresses the CPU can generate. Thank you.